Welcome, in this one I'm going to show you another proof from topology. So it says here let P belong to G where G is an open subset of R2. So let's stop right there because that's already telling us a little story. So here's a potential picture. Okay, this is just a picture to kind of help us understand where we're beginning in the proof, so it's visual. So I have here a set. You can basically just trace it and notice that it's open, meaning that it looks like the one that you see here, right? The border is not included, it's dashed. So that's my set G, and inside there somewhere is a point P. That's what this says. Let P belong to G where G is an open subset of R2. Already a step forward. Next, then there exists an open disk D such that P belongs to D and D is a subset of G. So we have to prove the second part, that such a disk exists. Okay, so let's go to the proof. So by definition of the interior point, there's a disk D sub 1 at first, such that D sub 1 is the set of all Q, and R2 such that the distance between P sub 1 and Q is less than R. So look at this modified picture. The pictures kind of correspond to different stages of the proof. Here is now P sub 1, some different point, different from P. Here's Q in that position somewhere, okay? R is the radius of this inner disk, and now the whole disk is named D sub 1. And notice that clearly P belongs to D sub 1 because P is inside that disk, and D sub 1 itself is a subset of G, because D sub 1 is inside the G sets there, as you can see. Continue next. Here's the heart of the proof, essentially, at this point. So what we're going to do is focus on this next bit of information. So D, remember, we're looking for D, right? Because remember back to the original statement of the question, it said, prove that there's an open disk D such that P belongs to D and D is a subset of G. You see that? So we're looking for that D set. So I'm going to define D to be the set of all Q belonging in R2 such that the distance between P and Q is A over 2. So what is A? We have to define A meaningfully. Look at this picture. I'm going to zoom in here, right? We need to decipher this because this is where the magic happens, really. So P sub 1 is at the center of the disk D. P is at the center of these two concentric disks that are open also. Now A is defined as R, so R is the radius that goes from P1 to the boundary of P1 essentially. So R minus the distance from P to P sub 1. So this quantity right here that I'm tracing above my head, right, that's the distance from P to P sub 1, from P sub 1 to P, that's the distance. So A is defined to be the difference of those two things. So you can see that in the picture that would be indicated using this brace right here, okay? So it goes from P to the boundary over here, you see that? So that's why you need that A. It defines this quantity. But then beyond that, our D, the disk, looks like the following, right? It has A minus 2 in this position, not just A, because that's the distance between P and Q as we are defining it. So why is that the case? That's the case for the following reason. Look carefully. I'm going to take A, which is this bigger one that goes from P to the boundary of the bigger disks there, and I'm going to divide it by 2. That's going to give me the one that goes from P over to here. It's a smaller one. It's A divided by 2. And you can see that. It says A divided by 2. And notice that that disk contains the point Q still, and that inner disk is called D. So I've just constructed a disk around point P. Now notice something. That disk, D, is clearly a subset of the disk D1, and the D1 is clearly a subset of G. You see that? So what I'm saying as a conclusion, if you look at this picture very carefully, it's telling you the story. P belongs to D. D is a subset of D sub 1, and D sub 1 is a subset of G. Therefore, D is also a subset of G. You see that? So I've been able to construct this disk D around P that is a subset of the entire G by looking at this picture. It's all there pretty much. So the conclusion more formally is that P belongs to D. D is a subset of D1, and therefore D is a subset of G. And that proves what we set out to prove essentially. All right. Drawing pictures in topology turns out to be very useful. They can be very subtle though. So remember what we set out to prove. There's an open disk D which we have found now such that P belongs to D and D is a subset of G. We have proven exactly that if you look at the last line and last picture. Alright, let me zoom out. I hope you can still see all of the crucial ideas. I know they're kind of small. It's hard to fit everything. Thank you so much. Please leave a like and subscribe. I'll see you in another video.